So I will start slowly with a review and easy, and then it will speed up. But the slides will be on this data files, whatever, website. Okay, so starting slowly with the history, we know that it's common envelope. The common envelope event is some unstable mass transfer, which was inferred from observations of closed binaries of 50 years ago. Is it 50 or 40? Many, many years ago. We know that it's a rapid phase during which a smaller companion spiral is inward. It's assumed to terminate with either ejection of a common envelope or with a merger. And we know that it's a very, very good tool to transform initially white binaries into closed binaries. And most of people here like closed binaries, especially after all the discoveries which Liga did. Now, in cartoonish type, the common envelope involution looks like that. A little guy goes into the envelope, or a bigger guy, then it goes something like this, and the envelope boom, boom, and goes away, right? Easy. Okay, so what was invented many years ago, first of all, it was a shortcut from the initial stage to the final stage. You have your white binary here, and then somehow you do the shortcut to the initial binary. And to do so, it was invented an energy formalism. And wave handy, what does it mean? You take the energy which you think is available, and the energy that you think is available is the orbital energy, and you compare it with the energy that you think you have to spend, and the energy that you think you have to spend was called as a binding energy. That's easy way to approach. Now, then the people try to compare, it didn't really work out, and they introduced the factor which is called alpha. Physicists like different letters, and alpha is the first one, right? So that's why. Now, the alpha is efficiency of reuse. Now, one needs to understand that it's not really efficiency of using the energy, because energy must be conserved. We all know that. It's to account for the energy which we didn't account, okay? So nobody can say that you didn't use completely the kinetic energy of your orbit, or you didn't use completely the potential energy. No, it's impossible. No, it's just that you didn't take into account some additional energy sinks or the sources. So that's about as much as the word efficiency can mislead people in understanding what it means. Now, but this is where the theory ends. Okay? I appreciate the approach that organizers did about separating theory and the computations, but I think it's kind of misleading and wrong, because I don't want to talk about alpha formalism for the rest of the meeting, but without discussing computations, how they affect the theory, we cannot proceed further. Okay? So now, what we learned from some computations, and this is how the theory now progresses. We know that this shortcut, which usually been depicted on this stage, which is a plunging, and it's very short stage, it's only a part of a common envelope evolution. Okay, it all starts at the time when the initial mass transfer has been issued. And there is no such thing as immediate instability of the mass transfer. The instability can develop on a timescale of 10,000 years. So for 10,000 years, it can go on with a mass transfer rate 10 to the minus 4, 10 to the minus 3, which is higher than your thermal timescale mass transfer. But the common envelope evolution will not start yet. However, a significant mass of the initial envelope will be lost during that phase, and that will change dramatically the outcome if you will try to invoke alpha formalism later on. Then you have the moment then your mass transfer indeed become unstable. I call that the moment when you start to lose the mass through L2 or L3 points. Now that stage, at least according to my computation, is not very long. It might be taking longer in various systems, not in the system which I looked at. It usually takes a dozen, maybe maximum 100 orbital periods. And then you start the spiral in. Now, during these stages, it's when the most of the initial angular momentum of the binary has been lost. And that's important, it will be important later on. Now, so then we have a plunging, and that's usually the stage which is best to simulate because it's a dynamical. You can neglect most of other physics except for mechanical energy. So that's usually the stage which is tackled by computational codes. Now, however, once the envelope expanded, and if it expanded with the most of the mass a little bit above the 6 current orbital separation, then the forces which the binary can affect, with which the binary can affect the expanded envelope, going down. So the orbit and the expanded envelope have decoupled. Now, at the same time, it was invoked in the past in '79 by Mary Hofmeister, but you may well be moving into the regime when the orbital shrinkage will become comparable to at which rate the envelope can lose the energy from the surface. Now, your envelope is now expanded, the luminosity is higher than before, and it can lose a lot of energy. So this stage, it may continue for a while. We find that now that this envelope is not really stable, so some kind of instability will develop here and eject the envelope or collapse it back, whatever it is, but this stage is not exactly stable. Now, so what, the point which I wanted to make and ask people to be very concrete when they do their papers is that when you discuss your simulation or some particular stage of a common envelope, be very, very precise about at which time scale you are working at. Because every stage here has different time scales when a different physics has to be invoked. And you cannot say that you're doing a dynamical evolution for AGB stars because it will never be purely dynamical because your thermal time scale is comparable to dynamical event. And so you're losing a lot whether you do it just in 1D or in a 3D. Okay, so we need to be very clear about the terms. Now, the definitions on when you switch from one regime to another regime. I mean, I have my definitions, but I will be happy if we as a community will come to some certain terms on what we call as what. For example, here, I know that here is a pre-plunging, then I say, okay, assume that your energy over orbit changes at the rate about 10% per period, then if you have a plunging, then it's the rate of the orbital change is become less than 1% per orbital period. Then this is what is usually called as a slow spiral in by the most of the codes. Now, so here is the simulation which goes a little bit beyond. So now this is what is usually reported. And what is usually is when you come to the slow spiral, because 100 orbital periods here of this binary is about dynamical orbital period of an envelope, or few dynamical orbital periods. You are not yet moved into the slow spiraling stage. And if you say that I completed my simulations, no, you do not, okay? You need to check where you are. And it will be great if we will establish the criteria by which we will be reporting that this is the end or this is just beginning, okay? Right, so now a little bit of equations. I hope they will not really frighten you. So what is really energies that we need to talk about? So we have, if we will be talking in terms of this plan, of this shortcut from initial stage to final stage. So we have some initial thermal energy, potential energy, kinetic energy, and some extra energy, right? Extra energy could be anything what you want to use in order to eject the envelope if everything else didn't work out. So basically it's a fudge factor. But of course, everyone can make justifications to whatever directions as they wish. And what is usually included there is accretion, jet, magnetic field, nuclear energy, you can call it. Then the final state is again, it's a final internal energy because you should not forget about this, potential energy, kinetic energy, and energy that has been lost through radiation through the surface. Now, we also need to talk about the initial conditions at which we compare the simulations, because if you take your secondary jet at Rochlop overflow or when you have a companion just grazing the surface, the outcomes will be completely different, and there is no way around it. It's just because it's a different initial energy involved for potential and kinetic energy. Okay, so what's the problem? And so now I want to say that I'm actually very interested in transferring from big scale 3D simulations into the outcomes which could be useful for 1D codes, like MESA. And to be honest, it's because this is what I started with yet under Philip's supervision as a grad student. Now, we can look at the energies which we have in 3D and which we have in 1D and think about whether we can make a direct comparison. Now, so here you can write down your potential initial energy in different components, and then you realize, okay, so this is what is usually included in energy formalism. Binding energy of the envelope, binding, it's another problem, and this is what is included in the orbital energy. Then you can take here what you can call 3D energy of your envelope, and you can compare it to what you have in 1D codes. Now the problem is, when you deal with 1D codes, is that you have to use a thin shell approximation. It's spherically symmetric. Now you can calculate the difference between the proper 3D potential that you have in the 3D code and how your 1D code will see that. And the difference in the potential is about 17% for this particular system. It could be going from 5 to 40% for the system which I looked at. So the difference for the shells which are outside of the orbit of the binary is dramatic. Now you also can look at the kinetic energy. And kinetic energy is a little bit easy. I mean, you can write it down in the components, and in principle you can calculate kinetic energy properly in 1D code if you will assume some Roche-Low approximation. The problem here comes into that you don't really know where to put that energy in. And I know that because I've been placing that energy according to all recipes, and that will be mainly around the orbit or inside the orbit. But if I look on what my 3D code does, it's not where it really works. It usually works outside, and that's not very intuitive. Okay, so the thermal energy, it's another problem, right? So internal energy in principle for initial system consists of several components. It's a thermal energy, which is a microkinetic motions of the molecules plus radiative energy. This is the energy of recombination, which we cannot forget, because when the hot plasma recombines, it releases some energy. Okay, it's a different question whether you can use that energy, but that energy is there. It's potential until it's triggered. And there is also internal energy of the core of your star and of a companion. Now, the simplification which is usually done is that those energies are the same at the start and at the end. And they are not the same. They don't have to be the same unless your cores and companion are completely degenerate and did not modify whatsoever. But if you have a common envelope, for example, with a main sequence star, and your giant had a non-degenerate core, that is not guaranteed. You'll have an energy flow from one to another. Okay, so now the problem also with 1D codes is that what I see from 3D simulation is that the Pelagian phase usually takes place at the order of initial orbital period. The orbit, the change of the orbit during that time is non-Keplerian because the mass is changing inside the orbit. You cannot have a potential which will be Keplerian. And so you cannot really do the same approach as it's usually been done in the past with 1D codes. So somebody has to think about it. But in principle, I think that a Pelagian phase is not possible really treat in 1D codes. Okay, so the energies at the end of a story is also another thing. What is usually, so again, you can consider as the ejector, so internal energy, potential energy, and kinetic energy. What is usually only taken here is that you have the orbital energy of your formed binary, and it's completely ignored to have the internal energy of ejector, potential energy of ejector, kinetic energy of ejector, the radiated energy, and the kinetic energy of a center of mass of a binary that is formed. So all those terms are ignored. Okay, well, it's less important, but I think I was talking already too much. So here is the list of all ignored terms which I've been talking through and where they can be kind of ignored or non-ignored, just to make sure that you realize that when you use a simple energy formulas, this is all what is ignored. Now, I will concentrate now on something which I have taken from my simulations just to evaluate whether those energies terms are negligible or they really have to be taken into account. Yeah, and of course, the thermal time-scale instability and establishment of stationary outflows also modifies everything from energy formulas. Now, okay, so the first thing which I want to say, so my group have made some simulations for the common envelope evolution where it was a full complete ejection. And what we took from there is that we found what's the energy the ejector takes away at infinity. Okay, because if you think about the energy formulas implies that the energy of ejector at infinity is zero. Basically, it's like a perfect fine-tuning which nature will never give to you. What we found is that when the ejector is away, it carries between 20 and 50% of the final orbital energy, so that the energy that it takes away at infinity is not negligible at all. And the outcome of the common envelope evolution will be different whether you apply just direct formalism or the formulas where you take into account the energies which comes to with the ejector. In some sense, of course, you can say that it changes your alpha to a half or so. Now, obviously, I'm one of those people who work on the recombination, and so I just a little bit to explain how it works. So the important thing to understand is that the recombination is a potential energy. It's not the energy which is given to you right away. You have to trigger it, and what is most important is that it's important to trigger it when it actually can do something. What I call as a recombination radii is the radii above which, if the atom recombines, this energy is higher than the potential energy. If it recombines before this radius, then the potential energy is too high. It will not go to infinity. It cannot. It's not enough energy. If it recombines above, it can. So that's the first condition. But the second condition is whether you can capture that energy, and it will be not lost immediately. And again, that's a condition which has to be checked. In the cases when I modeled it, the recombination radius is here. The recombination takes place here. So here is shown the envelope, which is still bound formally. The recombination continues. Here is about 20% recombined hydrogen. So when it recombines here, it's already unbound. But here is the radius when the optical depth is more than 1,000. So it's really easy to capture that photon, the optical depth at this particular frequency. Now, how much time I have?
You got plenty of time.
Okay. Then I will go a little bit more on the recombination. So that's about physics. It's not really computation. One needs to understand that the energy which is released from recombination can be taken away by two mechanisms. One is radiative flux, and one is convective flux. That's physics. Now, one can look at the equation of states, and what I'm showing here is basically the plane of equation of states plotted on the density versus temperature. There's absolutely nothing else involved, right? No common envelope simulations, nothing else. It's the equation of states for the given chemical composition. With the colors here, is showing opacity, and with the lines here are shown the lines of a partial ionization of hydrogen, where they are located for this particular stellar mixture. Now, one can see that the hydrogen usually combines, obviously, in the places of a high opacity. This is coupled, right? And this is why we have opacity is high. Now, we need to check whether the radiative flux is capable to take away this energy or not. First of all, we can compare the ratio of radiative flux at this particular place to the convective flux. We can remember that radiation is usually subsided compared to convection if opacities are high. So one can expect that convection will be prevailing there. And so here, what I'm showing is the ratio between the radiative flux and the convective flux for each place on the equation of state plane. And what one can see is that for gravities, which are for giants, like normal for giants, like even not very expanded, the ratio is usually everywhere here is much less than 1. Which means that we can forget now about radiation and switch to convection and check whether convection is capable to take the energy away. Again, this doesn't take yet into account any stellar structure or common envelope structure, it's just purely what comes from the equation of state. Now, one can calculate the maximum convective flux. What is maximum convective flux? This is a strange thing which never takes place in nature, I believe. It's when you evaluate how much energy can be taken away by convection if convective elements are moving at the sonic velocity. Now, one can recall that the convective theory has been derived in the approximation of very, very subsonic motions. So in principle, our convective theory is not applicable to the maximum convective velocity and how much convection can take away from the maximum convective flux, but let's assume that we can do that. And so here is shown what's the maximum convective flux could be everywhere on that plane. So now I'm coming to a little bit of the estimate, and the estimate comes from, now you say, okay, assume that my recombination energy is released at the order of a local dynamical timescale, as it happens usually during the common envelope event, but again, it's assumption about dynamical, and that will be the ratio between the energy released through the combination to the maximum convective flux locally. And for all the places where the hydrogen can recombine, except for here, but it still has to propagate to this direction, the ratio is way less than 1. Now again, the maximum convective flux is not reachable. What one can evaluate, actually, it's a very funny thing, is that you can take a stellar structure and you can look how much energy you need to add to convective eddies in order to start them moving at the sonic velocity. When you do evaluate that, you understand that you have to plug all your recombination energy in your local convective eddies in order to make them start moving at the sonic velocity, because they cannot just move, right? It's an energy. What we usually forget about during the stellar evolution is that when the convective envelope operates, it stores the convective energy in. We usually neglect it because that convective energy doesn't change much from the model to model. But if you change suddenly from normal convective motion to this maximum convective velocity which you try to evaluate, then you understand that the amount of energy is dramatic. Okay, so now another thing is that understanding the mass ejection. So why mass ejections are important is because this is what forms the planetary nebulae, which observers can see later, right? What I see from my simulation, so this is kind of a Kippenhahn diagram where only the bound mass is shown. So this is initial mass, 1.8 solar masses. This is evolution through the common envelope evolution. And so there's a several ejecta. One of them is when you take away most of the initial angular momentum. Then you have a plunging during which you take away a huge amount of mass during a short amount of time. Then this period of time is then the recombination starts to work. Now it seems to be shallow here, but in the models which I looked at, it operates between 0.15 and 2 solar masses a year. So it's not that small. Now the interesting situation is here, which I call it the shell-triggered ejection. So assume that you have recombination outflows working out from your envelope, but your envelope is still bound, right? What does this mean? The envelope is at its parabolic trajectory. The parabolic trajectory means exactly this, right? So it recollapses. When it recollapses, it triggers a shock. And that shock triggers another ejection. So then it again moves to the next stage of recombination outflows. Now, interesting thing here is that, so the color here shows the relative change of the entropy as compared to the initial entropy in the same envelope. Of course, the colors here are vast, but in principle, the relative change of the entropy is very small. And then I'm saying very small, I'm comparing it to the outcomes of 1D codes when they try to inject the energy inside the common envelope. Now, so what I found is that in 3D evolution, you usually, when you inject your energy self-consistently, it's mostly mechanical energy. It doesn't really transfer in the thermal energy, and this is what we want. However, in 1D codes, we only can insert the energy as Q, as the heating, and that heating operates to change the entropy. Now, I tried a lot trying to inject the kinetic energy in massa, and I failed. In fact, it provided absolutely the same result as inserting the Q, like the heat, and it always changed the entropy. Now, why it's important? Well, it's important because it changes at which radius from the center the matter can recombine. Okay, so literally it changes the outcome of the common envelopes. So, I mean, formally, the envelope will have the same energy, but in principle, it just will start to recombine in the different positions, and as a result, you can have either outflow or no outflow. So here is a profile of an ejector at some point after the common envelope evolution finished, and this is just to show you that this is an imprint in the velocity, which we can see. You can also see that velocities are not the same, so in some time in the future, this will kind of moved into this place, etc. This is the initial ejector, which takes away most of the angular momentum. This is the density. It's decreasing. So I hope that people will calculate the post-planetary nebulas using this ejector at some point. We cannot with our codes. Our codes operate on a dynamical scale of an internal binary. Now, if you look roughly 1,000 days after, you can say, okay, it maybe look like a planetary nebulae. It's roundish, it's nice. Now, that's one of the pictures, right?
This is your shell bounce?
No, it's well before, because it's only 1,000 days after. So it's no far evolution. Now, that's only one picture, right? Interest 4, we analyzed many simulations.
Sorry, is that the common envelope ejector, or is that a...
So here is a common envelope ejector, here is a real object.
Okay.
Sorry. This, I don't know how many years after. This is 3 years after. Now, some simulations, although, shows non-uniformity. For example, here we have kind of a jet-like ejector on only one side. I cannot say exactly why it happened. Here we can have some double shell structure instead of one shell. There was 2 shells ejected. They probably will create a very nicely looking system afterwards. But interestingly enough is that you can see that this is in the XY plane. It's in the orbital plane, and it has some, this is the XZ plane. So it has a kind of a jet in this direction, and this is in the orbital plane, so it has 2 shells going this direction. I just cannot imagine how it will look like in the 3D many years after, but it will be probably not exactly spherical. Okay, now, so the angular momentum. In the very, very past, when I studied 1D common envelope evolution, I've been conserving all angular momentum which was created by the binary. Now, what I see from my 3D codes is that during the initial plunging, well, actually before the plunging starts, most of the angular momentum is lost. So the common envelope, even during the merge or slow spiral in, is not really rotating fast. And interestingly enough, I was not capable at all to find a simulation in which the internal part inside the orbit will be co-rotating with the orbit. So for the most part, there is some angular momentum in outside, almost none inside. It's just something to take away. So this is a comparison between the what is found in 3D, and this is a Keplerian. This is what it would have if it were rotated Keplerian velocity, and it's always much lower. Now, so during the end of a slow spiral in, most likely will end with one kind of an instability, and Matthew Clayton did a very nice simulations with MESA 1D when he injected the energy. and tried to look on what will happen to the envelope. So he created in the result a long-term variable which will be rotating like this in the Hedgeman-Russell diagram plane. It will be going through the periods of a high luminosity and periods of a very low opacities and low temperatures where all the energies will be radiated away. And so this is where I believe what we will have the shell-triggered ejections which we observed in the 3D code. But the full coupling between 1D and 3D never happened, even though we observed more or less the same events. So that's probably the ending, and it will be long term with many, many ejecta. If you saw objects like this, maybe it's exactly what it is. Okay, so now we'll move a little bit on into the observed thing, because I like this system. It gave me lots of hints in the past. This is V1309 score. It has been observed in 2008 to go through some outbursts. It's actually been reported by amateurs. Later on, using the database, they discovered the previous observations, and from those previous observations, they have derived that the system was a binary with a depleting orbital period. So it's an amazing system, right? Now, so what we know from the system, roughly speaking, is that it has increased in its radius by a factor of 100 and the luminosity of 1,000 very quickly. Then it had something like a plateau phase. Then it's very quickly declined from the high luminosities. The velocities which being derived from the radius of the photosphere expansion and from the spectral line's velocity being completely inconsistent. Spectral line velocity being much higher. So that led me to think that it's related to what is called the cooling wave front recombination. So the idea is that you have some hot, high opacity material where you have no radiative cooling because it's a high opacity. Then on the top you have some cold neutral environment which is transparent. You have very complicated photosphere between, where everything happens, your recombination, complicated radiative transfer, everything that you cannot treat. So the direction expansion is this. This is a mass ejection, but temperatures stay roughly the same here. So this is direction of a cooling wave propagation, and as a result, the front which you can observe stay roughly in the same space. This is what provides you with a plateau. So the radius and the temperature of the sphere remains roughly constant. Now, if I take the same picture which I showed at some point before with recombination, it's tilted down just to show that the recombination front stays indeed roughly in the same position. Okay, this is what we now see from a common envelope simulations. And indeed, so here is the photosphere somewhere above here because this is optical depth of 1,000. Now, my mistake was that I thought we actually can see into the recombination. Now, from my common envelopes simulation, I see that we cannot see into the recombination. We see much, much above, because the optical depth of recombination is extremely high. Now, we did some simple models, simple estimates, what it can be provided. So it provided some plane of where you can see those events, which can be called whatever you wish. Luminous red novae, intermediate luminosity optical transients. There were, I think, three more terms, which I never remember. So anyway, so those transits, it's kind of consistent. Although from now our current simulations, we know that the durations of the common envelope events, when you see them, should be longer than it was predicted by the simple equation which we derived many years ago. And the temperatures probably also will be below in the luminosity. So we're trying now to go into simulations and get the light curves of our simulations. Now there are problems obviously with that. One of the problems is that, okay, so me personally, I deal with SPH code. SPH code is a particle which has some non-zero mass, and those particles have usually a very high temperature. So you can try to look how you see your 3D star in SPH using the temperature of your particles. Now the central temperature of the surface particles, even though they're at surface, the temperature will be about 10 and 5 kelvins. Okay, so here we show a version of the same star. It's actually the donor for V1309 score, using the ray tracing technique to see what's the temperature will be appearing for those SPH particles. And the average temperature is shown here, is about 120,000 Kelvin. This is 10 and 5 resolution, 2 on 10 and 5, and here is a 3 on 10 and 5. This is from master thesis of my student, Roger Hatfield. Now, what we did instead, we created a method which we call it as envelope fitting, and I will not go much into detail because I allow my student to write it down before it will be copied by somebody else. But it's very simple, it's very powerful, and I hope you will write it soon. So here is shown the same temperature using how you can see the star using the envelope fitting routine. And the average temperature, of course, it's not exactly as in MESA, which is 5,000. However, it only differs by a few %, which I think is amazing compared that you started with 100,000 Kelvin. Now, using that routine and using that method for our entire V13 online co-simulation, which unfortunately is not yet fully complete, but anyway, so here is shown the temperatures of when you look on the orbital plane and XZ plane, and here is the light curve, which you can get from V13 online scope, looking at the equator and from the poles. So we start with relatively low luminosity as it's supposed to be, then we quickly grow. Our plateau phase is not yet exactly as it has been seen, but then it starts to drop quite quickly, and unfortunately this is where the simulations are now. Okay, so I cannot show anymore, but I hope it will be finished at some point soon. Okay, so that's my kind of final points about the current state as I see it and the things which we need to keep studying. My first thing is that can we try to do a wide across the board accepted definitions for stages so we can compare the results between the different groups. So when you publish a paper and I read it, I really know what you mean. Okay? Not that I try to send you an email, what do you mean by this or by that? So can we also adopt some minimum requirements for initial conditions, how to describe outcomes, so that always some minimum outcomes will be described, and we always can find it from those simulations. So as a result, also so we know that the common envelope projection can be modeled, at least for low mass stars. Yeah, I only work with low mass giants, but this required the creation of states. Recommendation helps. In studied cases, I cannot say that it will be guaranteed to work and help the ejections in all the common envelope cases. Every single case has to be analyzed separately. Some mass will be always ejected, even in case of mergers. So for example, if you work with binary mergers and try to work on your merger product, it will be not M1 plus M2. Substantial mass can be lost even before the common envelope merger event has started. That has to be taken into account, and I think this is understudied at this moment. It may change dramatically the outcome. Also, L2, L3 mass transfer is not studied well enough. We don't, I mean, there are some analytics, very old, I will say, not very convincing. There is almost no simulations. For 1D evolutions, I mean, of course we want to do 3D evolution, but we cannot do 3D evolution for all possible cases. So we need to find a way how to model it in 1D. So we need to somehow create recipes from 3D for 1D, for timescale for 1G, how to inject, sorry, it's, shall say, mechanical energy, how to lose angular momentum. And so also I would say that the merger products will not rotate very fast. 3D envelopes are not as heated as usually in 1D code. It all creates problem, and we need somehow to fix it, to mock models, to mock the common envelope models in 1D. Modeling light curves is very important because it's the only way how we can probably compare what we can model with what nature does. And I'm very happy that many people work on it. That's all. Thanks.
So in lieu of questions from Asha, let's proceed to the discussion modified Philip.
Yes, thank you, Natasha. I think Natasha introduced the problem very well in the sense of how problematic it is, how many length scales and time scales are both different physical processes. And so I think for me, one of the questions for this workshop is, how long will it take to solve it? Can we put it all in one calculation? My feeling is that probably we would have to wait a few decades for that. Or alternatively, which is the approach I and Natasha have chosen is perhaps we can split it up into simpler problems, which we can do already. And that's perhaps one of the part of the questions discussion I want to start now. But before we get to that, I'm sure there are plenty of questions for Natasha and also probably comments. You haven't even mentioned magnetic fields.
So in transient observations, you see the development of a spectrum of H-alpha lines in emission, and the photosphere is at about 6,000, which is about the recombination temperature. And then those lines are quite broad. They're about 100 kilometers, indicating that that material is already above escape speed. So while I do agree with you that when you look at the simulations, it looks like where the recombination energy is very, very optically thick. The observations seem to imply, maybe Nadia has a comment here, that there's emerging radiation from the recombination front, and at that location, you've already ejected the material.
So, I mean, as I said, systems are different, right? So I only...
So this would have been like, these are a bunch of systems that Nathan Smith was talking about, so a little bit massive. So we know that as soon as you go to different parameters.
So if I will go to the plot which shows where it can work, recommendation, so the reverse thing. So, yes. So in principle, the best thing is to show here. So this is the place where it can work. The thing is that, so here, you move into the plane in the equation of state where you can escape when you recombine. Now, it can be achievable in more massive stars than 6 solar masses and 400 solar radii, just because the initial entropy here is higher. So I have some criterion for the entropy, about 37, whatever, moles per blah, blah, blah. I mean, standard definition. So if the entropy in the envelope is about this, then it can escape. Okay, but it's bound to that entropy. Now, it is possible that you somehow heated the envelope through shocks, which we, for some reason, do not see that heating in our simulations. Maybe then it also can escape. But as far as I see from the equation of state plane, it only can escape in this place.
Just a comment more than anything else. I mean, so I think what this points to is really, you know, when we think about different problems we have to include, is how do you include radiation transport in these incredibly complex systems where we're going to have, you know, we're going to be very optically thick in places, and then there may be other places, especially if you're generating, you know, a lot of density inhomogeneities where you're going to be switching over to optically thin. And so I think there's some conversation here about, because really we won't know the answer to the recombination until we can actually do the radiation transport as well and know where is it actually being lost. So I think that's just an open topic.
Well, this is exactly what I'm showing. I mean, you know where it can be lost. I mean, you can look at the equation of state plane and you can see there. If your star during the common envelope evolution moves into this part, you will lose.
Right, but
if it does not, you will not. I mean, there is no way the radiation transfer will work.
That's what I'm saying. But you don't know prior where what the density distributions look like. You know, you have to do the 3D simulation to know what your density distribution is going to look like. You know? And particularly if you have things like jets, if you have accretion going on, you're going to end up with an even more complicated density distribution in your 3D simulation than we have now. And it's already pretty complicated.
I think one thing that the F ratio leaves out actually is, and since it's derived from dynamical time averaged and
no, here there's no dynamical time average.
Well, in your paper,
it is here.
No. In your paper, it's. I mean, obviously you can construct an F ratio the way you have, no matter what. But convection and radiation diffusion are not the only ways that that energy gets transported out. You can also advect. You can move stuff out to lower densities, and so you could move from one place in that diagram to another where radiation diffusion can occur more readily. And I think that's kind of what Adam's getting at. That's not included in the 1D models, and it's not included in the 1D approach in your paper.
Again, this plane is model independent.
I know.
Your model can move from here to here, and then you can see whether your radiative transfer can take the energy away.
Right. Yeah.
That's what I was saying, right? But you are confined to this plane. This is equation of state, unless you say that the Thomas didn't calculate the equation of state.
The question is whether, how does the model evolve in that plane?
Right.
Yes, that's a different thing. That's what I say. I have a criterion with the entropy, which is related to that.
Mhm.
So you can move here. If you know that your model moved here, you can look at this, then yes, radiative transport. If it's not,
Right.
So, I want to get how important radiation really is, right? So Natasha made the argument that basically photosphere the photosphere is like 1,000 tau relative to the recombination region, right? So like, if it's so optically thick, why should we ever care about radiation? Because like if we're looking at simulations look at physics on dynamical times, like this thing looks like more or less like trapped radiation.
Well, it depends on the system, like she said. I mean, there are some systems for which, the diffusion, for massive stars, the diffusion timescale is short.
yeah, with massive stars, you will be here.
Okay. Certainly radiation will also be important in connecting to observation, right? That's clear.
Well, from the point of view of observations, what we see are molecules and dust, and this is, I don't know if somebody has treated, also like radiation on dust, and how that, it's absorbed the envelope, because, that is dust. That's, yeah.
So the dust forms a bit later typically.
Yes.
Few hundred
Yeah,
years later, not
you may want to talk to Joe, because Joe Chen, my postdoc, because he really now tries to work on whether he can capture the energy from recombination from neutral state to molecules when he forms tests.
But by the time it's forming, the thing is unbound at that point, right?
Not necessarily. You don't know, right?
Yeah, not necessarily. It may be still bound but far away, but you can unbound it.
And there may be large free ejecta before the.
It could be marginally bound, just at the moment.
So you were showing like your this recent stuff with Roger Hatchbull, and your outermost SPH particles are already they're still way too hot to make dust, right? So
Oh no! We do form dust, but okay. So we should be forming dust if we will be forming dust. His equation of states do not include yet transition to the dust. He only uses the
okay,
opacities.
but your outermost SPH particles were 10 to the 5th Kelvin.
Okay, the outermost particle in SPH, when you don't use the envelope fitting, has a central temperature of 10 to the 5 at the start. This is for the star, for the initial star. Normal star has a temperature 5,000 Kelvin. So the envelope fitting tries to calculate the proper temperature at which you will observe that particle. Okay, so not the central temperature.
You mean of the SPH kernel? Of particles?
Yes, the central temperature is the SPH kernel. As you go through simulation, the core temperature, of course, drops down. At the end, it's less than 100 Kelvin for those who were ejected.
I see.
So it formally has to form the dust, but we're not taking into account it yet. The opacities are taken into account, but his equation of states do not take into account the energy which can be released from the transfer from neutral to molecules.
I don't know if this throws yet another spanner into the mix, but if you look, so we reproduced your simulation with recombination energy, thank you for the star, which works pretty much like you have, and we also have the one solar mass, the Passy star, the same time. And if you look at the opacity distribution, it's true that if you integrate from the outside, you're optically thick, but that initial opacity is kind of molecular and dust opacity. Then you have an optically thin layer slightly below that, and then it's optically thick again. And that would imply that you have some free streaming photons somewhere in the mix, and then they hit this wall of kind of dusty stuff, and and this is kind of early on, because as you know, we all simulate only the very initial phases. So that would complicate things even more if you had layered opacities.
And that's actually something we also found in the 1D calculations by massive flattening.
Right.
So we have this object thin layer and object thick.
I have a comment. Actually, I find that to calculate the molecular opacity or any opacity and the dust opacity, the first thing is to know whether dust and gas are in local thermal equilibrium, or dust is in thermal equilibrium with the radiation, because it absorbs radiation and it radiates away. It may reach its own equilibrium, and it may have a different temperature from gas. and that will affect the opacity we're talking about.
Just another complication, yes, thanks. Okay.
So I should mention, of course, we suggested that the importance of dust, right? We know that dust, the main mechanism suggested for HEV envelope projection is through dust-driven winds, right? Following the common envelope evolution, even without recombination, right? You puff up the whole envelope, and actually most of it is beyond the radius where the temperature is low enough to form dust. It actually looks very similar to an HEV star to some extent. So you should have tons of dust, and they are below most of the mass. In principle, all this dust-driven wind mechanism could start drive all this mass outwards. Of course, on much longer timescales. So that's one of the main differences compared to dynamical timescales that are relevant for projecting mass during the plunging, for example, or something like that. But dust is actually critical. You know, it's going to dominate the opacity completely for most of the mass following the heat spiral. So any kind of interaction, any kind of energy calculation have to account for the dust. If it's a combination energy, it can help capture it in some sense. But in any case, dust is really critical, and all these dust-driven winds have to be involved in all this common envelope projection in some